Here's what I have for magnetism. What I did is I went through the electromagnetism quiz and the magnetism quiz and the magnetism test. And I kind of like wrote down the common things that people are missing and like kind of the big idea kind of things. So that's where I got these kind of points or whatever to talk about. That's where they came from. So so the first one is that magnetism is like a field force. We have what we call contact forces and we have field forces. Field forces means that you don't have to touch in order to be affected by it. So for example, like gravity, gravity is a field force. There's not like a specific place we have to touch to be affected by gravity. It's just everywhere, and as long as you're, within the gravitational field of the Earth, you're um, you're affected by gravity, or gravity affects you. So that's kind of how magnetism is. Two magnets don't have to actually touch each other to be affected by the magnetic force, right? They can be close together. And have you ever put two magnets kind of close together and you can kind of, like, especially if they're the same ends, like a north and a north, when you try and push them together, you can kind of like feel them trying to hit each other. Yeah. Yeah. So even though they're not touching each other, they're still like interacting with
like
each other, and they can,
away.
they know they're there. So that's kind of how magnetism is. When we draw these field lines, let me see if I can get here. We like to draw them from the north to the south. So let me see if I can do my little pen. So let's say this is our magnet. I'm not a very good artist. So we've got north to south, and our field lines like to go from north to south, so they'll go like this. And then they'll go like this. That's okay, it went off the page, except it never came back. And then they go like this. That didn't work very well. They don't usually go over the magnet like that. And they just kind of go from north to south. They just keep going, 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 going. I think I might have a picture somewhere. Let me see.
Okay.
That might make it easier to see. So this is where I keep all my stuff for our class. Okay. I'm going to search. Okay, so here we go. Here's a, do you see these? Do you see how like when they're really close to the end, they're close together, and then they can kind of spread out, and then they get closer together again? Oh, sorry. Okay, let me, sorry. Sometimes I forget I'm not screen sharing anymore.
I'm still seeing the drawing.
And then I like, okay. Do you see this picture? Okay, so these are little like magnetic filings,
Okay, I see.
but they put them here. You can put them by a magnet, and then they'll line up in the magnetic field, so you can see the magnetic field. And so when they're really close together, that's where the field is stronger, and then when they're really far apart, that's where the field is weaker. So you can kind of see like in between these two, it's pretty strong, and like it looks like in the middle it's more strong, and then it's like on the sides in these it's not very strong. But a lot of times I'm just gonna Google to try and get some good pictures, because mine were really bad. Let's give you, okay, do you see these diagrams right here? Can you see all these pictures of magnets? Okay, so do you see how like at the edge of the bars, they're like all the lines are really, really close together, and some of them even like start touching?
Yes.
Like in this one right here.
Yes.
That's where the field is going to be really, really strong. And then do you see here, as we get farther away from the magnet, these lines get farther apart?
Yes.
That means the field, like here, the field is less strong here. Do you see this little hand? The field is less strong here than it is right here. and it's really strong right here. And it's more strong here than it is like way out here. So which makes sense.
Yes.
The closer you are to the magnet, the more strong, the stronger your field is going to be. Um, so
Okay.
let me get back to our little wherever we were. Okay.
Okay.
Okay. Um, so and then the lines, they're going to follow the shortest possible route from north to south. So you notice in none of those pictures did we have something, we didn't have a bar, and then, the lines weren't going like this. You know what I mean? They were going like from one side to the other, from one side to the other, from one side to the other. So they follow the shortest possible route. They're not going to be all squiggly and stuff. Um, let's see. Um, an element that is ferromagnetic is an element that is going to be like a permanent magnet, something that can form a permanent magnet. And
Okay.
so this really only occurs in metals that have unpaired electrons because it allows the electrons to form these like magnetic domains, which I'll get to. But it allows all the atoms to kind of like align their magnetic fields in all of these unpaired electrons, which then makes them really strong magnets. And so most common are iron, cobalt, and nickel. There might be other ones that can be, but I don't usually hear, mostly we hear about iron magnets. I'm not like the world's magnetism expert, so there might be another, metal that you could be a magnet that could form a ferromagnetic or a permanent magnet, but mostly we just hear about iron, and then cobalt and nickel can as well, but mostly we hear about iron. Sorry, sorry about my kiddo. um, and then so and then you can have like diamagnetic, which I hope I'm pronouncing it correctly. Let
Okay.
me. My mom's trying to watch him here
Okay.
at the hospital, and he's not having it. Um, magnetic. So this means there's like no magnetic field. So they're like not magnetic at all. Diamagnetic. And so the ferromagnetic
Ah.
are permanent magnets. Um, so let me go back to my review again. These are all the notes I took. So in order for a charged particle to produce a magnetic field, they have to be moving. And so
Okay.
when I used to teach in like the physical classroom, we used to take like D batteries, and we would turn little pieces of copper around a pencil to coil them, and then we'd attach them on either side um, of the battery, and we could get them to spin, and then with some magnets, and it would basically create a magnetic field. So we would kind of create like a little generator or a little motor um, to kind of demonstrate that. But in order for you to produce a magnetic field for charges, they have to be moving. So there's got to be some sort of movement somewhere. And then we have a couple right-hand rules.
Okay.
Um, I'm not gonna lie, I sometimes get them confused because there's more than one. But basically, um, when a solenoid would be like that coiled piece of wire that I was talking about that we would make for our little magnets for our class, that was a solenoid. So if you grab something like that with your right hand, and for some reason, usually because I have my pencil in my right hand, I tend to try and do the right hand rule with my left hand, and then I get the answers wrong. So make sure you're actually using the right hand. And you just put your pencil down. I just now had to put my pencil down because I was trying to do it with my left hand. Um, so if you grab it with your right hand and your fingers are pointing in the direction of the magnetic field, so sometimes you can even pretend that your pencil is the solenoid. Your thumb is going to point to whatever is the North Pole. So like, for example, right now I just coiled my right hand towards my left. And so my thumb is pointing back at me. And so my thumb would be pointing to the North Pole, and my fingers that are coiling around this fake thing towards my left side, if that makes sense, is pointing in the direction of the magnetic field. Um, and then we have this other right hand rule. Again, your fingers are still pointing in the direction of the right of the magnetic field, which is the same. But now your thumb is going to be pointing where the motion is, and your palm is going to be telling you where the induced current is. And so I've still got my thumb pointing towards my body, and my hand, I've got it kind of curled towards my left hand, if that makes sense, like I was holding a pencil. And so my fingers are kind of pointing, going counterclockwise. And so that's going to be the direction of the magnetic field. The magnetic field is going to go counterclockwise like that. My thumb is going to be pointing towards me. So that's the direction of the motion. And then my palm is where the induced current is. So the palm is going to be my palm is facing towards the left side. So the induced current is going to go towards my left side. Let me see if I can. I'm going to try again and Google some pictures of that. I'm not even going to try and draw a hand because I know I won't be able to do it. But that way maybe we could see them a little better. Okay, here we go. Okay, so this is kind of what I was trying to describe. Okay, so this person is basically like, because the way they've got their thumb, in order for their hand to look like that, the person is basically towards like the top of the screen, if that makes sense. That's where the person is. And so, yeah, yeah, exactly. If you like were to turn this picture like 90 degrees toward the right, then it would be like you were standing on the right side of the, does that make
Okay.
sense? And
So if we
so
rotated
they've
it to
got
the
this
side,
solenoid. That's what
it would be as if we were doing it.
that bar is right there. And so you can see that the fingers are twisted around this way. And so that means the field is going to be going this way. And so that's what they've drawn here.
Yes.
They've drawn the field as going around like this. The current is going to be pointing where their fingers are going. Do you see that? The thumb is pointing along the direction of the current, and also, with some of the right hand rules, that can be the magnetic field or the north. So let me see if I can find the other kind. They call them like, there's like right hand rule 1 and right hand rule 2. And
yes.
sometimes these pictures are like totally confusing to me. Well, this is tiny. Left hand roll. We don't want a left hand roll. That's just going to make more work. Okay. I think that one that we already saw was the best one. Because yeah, all of these are kind of confusing, I think. So we'll just stop with the pictures while we're ahead. So let's see. Okay, so there's our right hand rolls. Okay, now another thing that they mention a couple times in the notes and then also on the tests and quizzes are electric motors and electric generators. So electric motors cause a current to run through a wire, which then causes a magnetic field. And then this field can be attracted or repelled by permanent magnets, which then will cause the loop to rotate more and drive the motor shaft. So that's kind of like what I had built with my students. So yeah, I was gonna try and draw it, but well, let me see what I can do. So we had we had our little battery like this, you know, and then we had like some tinfoil right
With
here,
the wire and pencil.
and we had tinfoil right here, and then we had this loopy wire like this, and we put some magnets right here. And so you had to start it with a moving magnet. So you like sometimes the act of sliding the magnet in there would cause it to start rotating. But once you got it rotating, it would, it would keep going. And so that it basically kind of create a little motor. Like your current would be going through here, and then it kind of it's almost like it would, once it started rotating, it would make it rotate more and more and more and more. So like the act of getting it started was kind of, difficult, but once you got it going, it would just keep going, 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 going. So that's kind of how a motor works, which is kind of the same thing, right? Like inertia. If you remember that from physics A, the you want to stay at rest if you're at rest. So that's kind of how the coil wants to stay at rest, but once it gets going, then it gets going and it's, it moves pretty well. A generator then is going to convert mechanical energy into electric energy. So that's why, people plug in generators when their power goes out or whatever, because they're taking that magnetic energy, mechanical energy, and they're turning it into electric energy. So then you can run your appliances or whatever you need to do. And they have this word called an armature right here, and that is a rotating loop within that generator. And the quizzes and tests seem pretty. They really want you to know that word, armature. And so I think there's a question or two about like what is the rotating loop in the generator called, or what is an armature, and then you choose it, the right one. And then the notes also mention Lenz's law, and I saw a few questions about Lenz's law as well, which is basically that the induced current is always going to be opposite of the motion, and there must be some sort of work done to overcome the repulsion. So there's no math for that. It's just kind of I call it a concept law or a word law, where you just need to know words. This magnetism test is a lot of knowing concepts and not so much math. Where like I felt like the last test, the electricity test, had quite a bit of math, especially with the short answer questions. This one doesn't really. This one still has, I think, 2 or 3 short answer questions, but they're all like words. So it'll say like, I think like, why is the aurora borealis not in Georgia? And then you say, well, Earth's magnetic field, doesn't work right to produce that down here. It has to be, closer to the poles, or something like that. So they're all word questions. There's not really a lot of math. They ask a little bit about Earth's magnetic history, like has have the poles of the Earth ever reversed, or um, was Earth's um, is Earth's magnetic field strong or weak, or that kind of thing. So there's a little bit of that, but it doesn't ask like how many times has it reversed. It'll just say like, has it reversed, or do you think it would be a problem if it reversed, or tell me why. Um, you know, do you think it would be bad if it reversed in the future? If it would cause problems or whatever. So there's not a lot of specifics about it. They do have this symbol, and they ask you about it in the test, but they also, they have some questions. They ask you what this is, and then they also have some questions about it. So they have these 2 symbols. I don't know. You probably haven't seen them in your notes yet, since you just took the electricity test, which is totally fine. They have these 2 symbols. So basically, these are supposed to be an arrow of like where the current is going or where something's going, like whether it's into the page or out of the page. And so what they're assuming is they're assuming that you have like an arrow, like, like Katniss or whatever. Um, do you know the Hunger Games? Have you seen? Okay, okay. So you've got like, one of these kind of arrows. So they're saying that if you're seeing the X, you're seeing this part of
Frozen.
the arrow. So that means the arrow is pointing into the page. Does that make sense? Because you're only seeing the back of it. So the tippy point is, through the page, has gone through the page. Now, if you're seeing just this part, they're saying that is
Yes.
the tip of the arrow, and so it's like the arrow has been shot and is like the tip is pointing through the front of the page, and so it's pointing out like at you. Does that make sense? So this would be the arrow pointing out,
Okay.
and this would be the arrow
Yeah.
pointing in. So there's a couple of pictures about that, and then they'll ask. I think there's even a question that asks, okay, what is this? And it'll show this picture. And what does this represent? And it'll show that picture. But mostly like in the notes and things like that, you'll see like they'll do
Yes.
like a right hand rule, and you'll have a thumb. Let's see. Let's say you had, the current going this way, and that's because your your current is going through, and so your current, I'm trying to say. So like the back of your thumb would be towards the back of your
It's
right hand would be
frozen.
towards you, and your thumb would be like going in the paper, if that makes sense. Does that kind of make sense? Oh, let me see. It's frozen. Can you see my mouse moving now? Can you see my mouse moving now? Okay. So let's say, like, let me draw this again. Um, so this would be like your thumb would be like pointing into the paper because like your
Yes.
thumb would be like the tip of the arrow, and then the butt of your right hand, I guess, would be like this part.
Yes, I can.
And so then if you did that with your right hand, um, it looks like
Yes, I
your
can.
current would be going, that way. Um, so that's those little symbols. I try to write them on the review, but I didn't do a very good job. And then the transformers, that's like that lab that we talked about at the very beginning of the session.
Okay.
Um, I have seen a short answer question on the test about these transformers, where it'll give you the initial voltage and it'll give you the lower voltage, and then it'll ask you like what is the ratio of primary turns to secondary turns. So if we wanted to work that out, let's say our primary voltage was I don't care, computer. Let's say our primary voltage was 240, and our secondary was, I don't know. I'm gonna do 24 just because I can do that math in my head. Um, so then our ratio would be like 10 to 1. And so for that type of question, it's either a short answer where you just show your work and you say 10 to 1, or it's a multiple choice and they give you a bunch of different ones. So you would just do like the 240 divided by 24. Whoa.
Okay.
Man, I cannot get these letters to write here. I'm on the public Wi-Fi. I wonder if that's why.
Okay.
And then they ask you like a horseshoe versus a bar magnet, like which one is stronger. And I think they say that the horseshoe is stronger because the two poles are so close together in a horseshoe. It like concentrates that magnetic force. Where in like a bar magnet, they're on completely opposite sides. The horseshoe
Okay.
makes those two poles real close together. So I think it says that those are stronger. So that's the magnetism review. And that I'm not saying that's like everything on the magnetism test, but it is a lot of it. And then I'm going to show you, I don't know if you've seen this. What is this doing? No. My computer decides it wants to update right this second.